Welcome to lecture 7. And the topic for today is basically the continuation of what we talked about or we have been talking about for the past few lectures. So far we've seen first order circuits to some extent. And I'd like to get into second order circuits today. And although these are listed as separate topics, and this is how you will see things listed in a book, for instance, what I hope you will agree with me, and I hope the way you will start thinking about these things, is that they're not fundamentally different. Sometimes compartmentalizing too much is not a good idea. And the approach to solving a second order circuit is no different to solving a first order circuit. It's just that you will end up with a differential equation that's second order, and its solution will be a little bigger, okay? But there is no fundamental difference as far as the laws of circuits are concerned. And so it's really maybe just you can think of it as a slightly more elaborate example. Let's take a look at a simple, pretty basic time-dependent circuit with a capacitor and an inductor, for which we'll see we end up having a second order behavior. And we'll see that the outcome would be perhaps a little richer than what you see in first order circuits. So consider this circuit. I have a resistor here, an inductor here, and a capacitor here. So the elements are very much the same kind of things that we have been using so far. Okay, so we have an R, L, and C here. And this would be a source voltage. In general, a time-dependent source. And let's assume that this is Vs is a unit step function. So Vs, which is a function of time, has been 0 for a long time. And at time t equals 0, in this case, jumps to the value V0, say 5 volts. And my interest is in calculating this current I as a function of time for all times. So we have had the circuit sitting for a very, very long time with an input voltage of 0, and at time t equals 0, the input voltage has jumped to V0. And we want to see how the current I, which happens to be shared among these elements, behaves as a function of time before that transition and after the transition, all the way to very long times in the future. Okay? So before I do it, I'll ask you guys to give it a try on your own. To come up, well, to write the laws of the circuit, to try to come up with a differential equation that describes I. And I'll tell you what the solution to that equation is. And I think you said that you have already started seeing second order equations in your differential equations. Is that correct? Yes? So hopefully it's familiar, but I'll write down the solution for it. So for now, let's just try to get a differential equation that describes I. Could you try on your own for a couple of minutes? Now, if you don't know where to start, maybe listen for a few seconds and I'll give you some guidance. So all we are trying to do is to come up with a differential equation that has I of t, that function. And you don't need to know this beforehand, but I'll tell you that you'll end up with a second order differential equation. And the way to get there is to write the laws of the circuit. Now, you have one loop and one KVL that will have VR, VL, and VC in it. And then you have to write down the element relationships. Of course, you also have the KCL, which really, at each node, if you write down the KCL, which we have done before many times, you will see that in this case, we'll just tell you that the currents are the same in all those three elements. And so that's why I just had chosen that one current. So if you write then the element relationships for each of these three, you will have ways of relating VR, VL, and VC. In that they will all be written in terms of I. And then by replacing things into your KVL, you should be able to get a differential equation for I. So try for another minute or so, and then I'll write it down. OK, so let's write this down together now. So first of all, like I said, we have one KVL here. And that's simply, again, the way I'm used to writing things, which for me is going usually clockwise. And if I encounter the negative sign of an element first, I'll add a negative here. Then plus VR plus VL plus VC equals 0. And like I said, KCL we have implemented automatically, so I'll say KCL is implied by the fact that I have chosen the same current for the elements. And then the element relationships, well, we have the voltage of the source, that's Vs, and that's a unit step function. For the resistor, we have a simple proportionality. For the inductor, we have the voltage being proportional to the derivative, the time derivative of the current. And for the capacitor, it's the other way around. The current, which is simply I in this case, is proportional to the time derivative of the capacitor voltage. Okay. Well, so you see immediately that all three voltages are related to the current I. And so if I use these three element relationships and plug them in to my KVL at the top, I have basically obtained an equation that has I only in it. Okay. Now, because the voltage is changing, there is a step function. Like we said before, the same systematic approach. We want to look at what was happening before the transition, so that then we use that information to come up with the initial conditions for after the transition. Okay. So now, before the transition, the circuit was sitting for a very, very long time with 0 input voltage. So the source was essentially a short circuit. Now, if the circuit was sitting for a very, very long time and was under DC steady state, what can we say about the capacitor voltage and current, and same for inductor? So, yeah. Well, let's not go too far. So how does a capacitor behave under DC steady state? There is no current going through it, right? And you see that immediately from here, because if there is no change with time, dV by dt is 0, so the current in the capacitor is 0. So there is no current in the capacitor, which means there is no current in the circuit in this case. And if there is no current in the circuit, so let me write these down. Before, or let's say t less than 0, for t less than 0, I'll say assuming we had a DC steady state. And this is what we've seen before, that a capacitor will act as an open circuit. So from the capacitor, just to highlight this, capacitor will give us I equals C dVc by dt equals 0. Inductor, on the other hand, will give us VL equals di by dt equals 0. Now, if I is 0, from here we can directly come up with the voltage of the resistor also, which is VR equals Ri equals 0. Now, if Vs is 0, which it is, VR is 0, and VL is 0, well, there's nothing left for the capacitor. So from these two, we also know that Vc is equal 0. So we see that all the voltages and the current are 0 before time t equals 0. So that's a relatively simple set of initial conditions, assuming we had a DC steady state, because this was sitting for a very long time. Now, after t equals 0, again, the main equations are the same. Capacitor, inductor, resistor, they are the same. KVL, KCL, they are the same. So basically from here, if I were to summarize, I of 0 minus is 0, VR of 0 minus is 0, VL of 0 minus is 0, and VC of 0 minus is 0. Okay? Now, immediately after this transition, when we jump from 0 to V naught on the source, what are the things that can change? Recall that a capacitor does not like a sudden change in its voltage, because, again, looking at the capacitor equation, that would mean an infinite dV by dt, which would mean an infinite current. Conversely, the inductor doesn't like a sudden change in its current, because that would mean an infinite voltage for the inductor. So now going to t equals 0 plus, capacitor does not like sudden change in voltage. So then Vc of 0 plus is the same as Vc of 0 minus, because there is no finite time difference between the 2 points, 0 minus and 0 plus. So that will still be 0. On the other hand, inductor does not like sudden change in current. So that simply means that I of 0 plus is the same as I of 0 minus, which is 0. So we were able to carry two pieces of information from 0 minus to 0 plus. One was the voltage of the capacitor. The other was the current of the inductor. Now, if you consider the circuit at time 0 plus, then we know that there is no current going through the circuit. So let me actually draw it. So the circuit at 0 plus at t equals 0 plus, only for that time. I'm redrawing the circuit. The value of the input has jumped to V naught. I have a resistor here, an inductor here, and a capacitor here. I just reasoned that the voltage of the capacitor has remained 0 only for time 0 plus, So here I have 0 volts. And I also reasoned that the current of the inductor is also 0 at that point. So this is also 0 amp. Notice that I have not a priori said anything about the voltage of the resistor or the voltage of the inductor, or in fact the current of the capacitor. These are things that I am concluding. Now, knowing that, and maybe I should have written this here to be more explicit, that this is really the inductor current that we know has remained 0. But knowing that, from our KCLs, we will immediately conclude that the resistor current is also 0, and similarly the capacitor current is also 0, only because of the way the circuit dictates things. Okay? I'm not making any general statement about the capacitor having 0 current because it has 0 voltage. That's not the case at all. In this case, it so happens that the circuit dictates a 0 current in it because it shares the same current as the inductor. Okay? So let's now start propagating this information. If I have 0 current, then what is the voltage across the resistor? 0 volts. No trick here. So 0 volts. Now, by KVL, if I have V naught here, 0 volts drop across the resistor, 0 volts drop across the capacitor, what is the voltage across the inductor? It will simply have to be V naught. Okay? Again, I concluded this from my KVL, which you might say I'm solving graphically on the circuit directly, because it's a simple KVL. So I'm not writing the equation. Okay? So such is the condition of the circuit at time t equals 0 plus. So you know the current is 0, the resistor has 0 voltage, the inductor has V naught volts, the capacitor has 0 volts also. Now that we know how things are at the beginning of the positive side of the time axis, we can start looking at what happens afterward. So now for t greater than 0. So t equals 0 plus was the first point for t greater than 0. So I should maybe say for the rest of t greater than 0. Okay. And my equations are up there. I'll bring them here just for a quick view. I have this KVL and the 3 element relationships. And all I want to do is to come up with one differential equation. So I'll plug in. Instead of VR, I'll put Ri for the resistor. Instead of VL, I'll put L di by dt for the inductor. And instead of VC for the capacitor, remember, now you have to do a simple integral. So from here, you could say, no, I'll write it down where we need it. So remember that we have our KVL minus V naught plus VR plus VL plus VC equals 0. We have VR equals Ri. We have VL equals L di by dt. And we have I equals C dVc by dt. From which then, if I do a simple integration, I get Vc at the time t would be, I'm running out of space here. I'll say Vc at the time t would be Vc of 0 plus, in this case, the starting point for me, plus 1 over c integral of I dt from 0 plus to t. So I will simply plug these 3 into the KVL. So putting VR, VL, and VC into the KVL, I'll get minus V naught plus Ri plus L di by dt plus that equals 0. Now, incidentally, in this problem, we just saw that Vc of 0 plus was 0 volts for this particular problem. That's not of a big consequence. So there you go. This is, in fact, a second order equation. Now, you might see a first derivative of I. You also have I itself, but you also have an integral of I. So maybe a nicer way that we are more used to would be reached if we just took the derivative of both sides. Okay? So take the derivative of both sides. So V naught is a constant. Its derivative will be 0. So you will have R di by dt plus L. Now the second derivative of I plus Vc of 0 plus was just a constant, the value of Vc at a specific point in time. So the derivative of a constant, again, 0, plus 1 over c. The derivative of the integral of I dt is simply I, the function I. And the right-hand side, 0, its derivative is also 0. Yes?
When you did the integral of the current, shouldn't it be minus Vc 0 plus? Because when you integrate on the side of Vc, don't you have to minus the term over?
Yeah, I've already brought it to the right-hand side.
Yeah, shouldn't it be negative?
No, so it's Vc of t minus Vc of 0 plus equals that. Right? So I've brought the constant to the
Minus?
If I integrate dVc over time, so it's the final minus the initial.
Oh, final minus.
Right? Very. Okay, so here you go. A second order linear differential equation. I will rearrange things to put the second order term first, to again make it look a little more conventional. And I'll also divide by L to, again, for just the purposes of looking like things that you're more used to. So I'll end up with R over L here. Here we go, a pretty nice looking second order linear differential equation for the function I of t. So now I'll be talking about how to solve this. But before doing so, a quick question. I'm just curious to see if this quantity here, if anyone has heard of this before. If you have done a project that has involved making an oscillator of some sort. Has anyone heard of, dealt with this quantity LC anywhere? No? So if you want to make an oscillator, a circuit that will go back and forth in time, so a voltage that goes back and forth. Let's say if you want to make a clock for a computer, you would need, so this would be one way to implement it. You would need an inductor and a capacitor. Maybe let me ask another question. Imagine for a second I put R equals 0. So if I replaced in that circuit my resistor with a wire, so R equals 0, no resistance. And if I followed everything else, I would get the same equation, but with R equals 0 here. which means the middle term would disappear. So then I'd have a second derivative of I plus some parameter multiplying the function I itself equals 0. Does anyone know what the solution to such an equation will be? So this will be, so imagine this is 0. So I just have the second order and the function itself. So what will the solution be for this? Yeah, so you can solve it in different ways using, let's say, complex notation and so on. But what will the ultimate solution be? Well, what is the second derivative of sine of something? The function sine. Sine. Cosine, right? What is this? Sorry, the first derivative of sine is a cosine. What is then the second derivative of sine? Negative sine, right? So if I had a sine function, if I took the derivative twice, I'd end up with a negative sign, right? Negative sign, and here positive sign. Now, if you had some constants in there that could deal with this multiplier here, you would be able to satisfy this equation. Sine and cosine. If I did not have this r here, the solution to this equation would be sine and cosine. This would be your basic oscillator. In this case, an oscillator implemented in the form of a circuit. And in fact, it's very common to see this kind of thing if you open a simple radio device, for instance, where you need, let's say a transmitter. You want to create an oscillation with a given frequency. You have an L and C. And now I'll write things down, and you'll see how this LC comes into play in terms of determining the frequency of that oscillation. But I just wanted to point this out before we launch into writing down the full solution for this. Okay? So now the solution in general for a differential equation. And I do realize you've seen this in your differential equation course, but for the sake of completeness, I'll include it here. So for a general differential equation of this form, for such an equation, so consider this equation, a second order linear differential equation for function x with the parameters alpha, omega, and gamma. The solution will be like this. If alpha is greater than omega, and this depends on the parameters of your problem. So the numbers in the circuit will determine what the value of alpha and omega are. If alpha is greater than omega, the solution will be x of t equals plus a constant, which happens to be just gamma over omega squared. Now these parameters S1 and S2 are as follows. Or I guess I can just write them in one go. If, on the other hand, alpha and omega were equal, give myself a little more space. then your solution would be like this. And finally, if alpha was smaller than omega, then the solution would be like this. And this omega d, the parameter defined here, is simply this. Okay? Now, if you have already seen this in differential equations, that's great. If not, it's a very standard thing, and to make yourself completely comfortable with it, all you have to do is to try these in that equation, okay? And you will see that it works. And by the way, you don't have to memorize this. If you ever need this, it will be available to you, okay? But you do need to understand it and be able to apply it. Now, of course, in your differential equation course, you might be required to be able to derive this, but that's a different. Now, so take this as a sort of separate box in parentheses. So a quick excursion to differential equations. And by the way, there are names for these that we'll soon talk about why. So if alpha is greater than omega, this is called overdamped. Is an overdamped case. If alpha and omega are equal, it's called critically damped. And if alpha is smaller than omega, it's called underdamped. But all this page is telling you is that if you had a differential equation that you got out of a circuit, and inevitably you will have alpha, omega, and gamma, those will be related to the circuit parameters. Well, all you have to do is to see which one of these three cases your particular equation corresponds to, and that would depend on the values of the parameters in the circuit, and then write the corresponding solution. Now you see S1, S2, and omega d, that are some of the parameters involved in these answers, are determined based on alpha and omega. But there is M1 and M2, for which I haven't given any value. Where should I find those from? Initial conditions. Is that what you wanted to say? Thanks. So M1 and M2 will be, in all cases, determined using initial conditions. Okay, so now let's take this and apply it to the circuit we have up there. In my case, for the equation I have up there, what is alpha? R over 2L, right? Because that coefficient that's multiplying the first derivative, we've called it 2 alpha. And I mean, you could have called it alpha, but then you would have a 1/2 in some of the cases here. So it's a matter of really having a clean notation. Okay. So for us, 2 alpha is R/L. What is omega squared? And that, now if you're used to using the letter omega for angular frequency, you know, if you have ever talked about sine of omega t or cosine of omega t, does that ring a bell? Anyone has seen it? Yeah. It's not a coincidence that we call this omega, because the frequency, at least you will see that has that the frequency has some connection to that omega. You see it here, right? So it has something to do with it. Now, alpha also plays a role in it. And finally, gamma, for our particular case, was 0. It just so happened to be 0 in that example. Okay. Now, you might say, well, yeah, that's very good, but I don't know which one of these cases our problem corresponds to unless I had some numbers. And that's the case, of course. We don't know. Without knowing what R and L and C are, we don't know if alpha is greater than omega or equal to it or less than omega. Okay? But so before doing a numerical example, which we will do now, I want to maybe briefly point out the form of the behavior of each of these. First of all, gamma over omega squared is just a constant in the solution. Okay, so it's not maybe terribly exciting. If alpha is greater than omega for the first case, these parameters S1 and S2 will end up being what? Well, alpha is greater than omega, so the square root is the square root of a positive number. Okay? A positive number that's smaller than alpha. Right? So then minus alpha plus or minus that will give you 2 different negative numbers. And if you then put those here, you have exponential of some negative number times t plus another term with an exponential of another negative number times t. So these are just 2 decaying exponentials. Okay? And so maybe the term overdamped makes sense there, because the solution to this problem is basically just, in the first case, a decaying exponential, or the sum of 2 different decaying exponentials with 2 different time constants, the inverse of S1 and the inverse of S2. If, on the other hand, we were in the case of the underdamped solution, alpha less than omega, then look at this frequency omega sub d, which is just the square root of a positive number. So that's just a positive number itself. And so your solution is in the form of a sine and cosine, so 2 oscillating functions that will oscillate for as long as you want. But then they are the sum of the 2 is multiplied by a decaying exponential. So you will have this form of a function that starts oscillating, but its envelope decays. Okay? So it basically gradually vanishes. So you'll have an oscillation like this, and it dies out. In the case of a critically damped solution, you still have that decaying exponential, but you see that there is a term, linear in t, that will want to initially increase the value. So you have some increase and then decrease. Okay? So this is just to give you a feel for what these look like in practice. Anything you guys would like to discuss here before we do a numerical example? Maybe I should again remind us that up until this point, everything that I did before giving you the solution to a second order differential equation, all the things that we did were just an exercise in dealing with time-dependent circuits. You can consider it as an example, as if we were doing a tutorial. Okay? So everything that we discussed in terms of the behavior during the transition, how to get the initial value, and so on, they're all applicable to first-order circuits too. Well, it's just maybe a slightly bigger example. So now I would like to do a numerical example. So maybe I should draw these. So let's say a damped, overdamped solution would look basically like a decaying exponential. But in fact, two of those with two different weights. Critically damped would be something like this, and I'm not doing a terribly good job at drawing, but you get the idea. And then underdamped would look like this. So basically you have some not doing a great job at drawing. So this envelope, if you want, is decaying. And in fact, you can see immediately the special case that I talked about. Imagine R was 0. The resistance was 0. And so R over L was 0, which means my 2 alpha was 0. If 2 alpha was 0, which then inevitably means alpha is less than omega, we are in this case. But if alpha was 0, this would be exponential of 0, which is 1. So I'd just be left with a cosine and sine. And that would be a special case where I do have this oscillatory behavior without the damping, without the decaying exponential. So this would just be oscillating continuously. Of course, if you could have a circuit without resistance. So like I said, I want to do a numerical example. But before that, let's also take a look a little bit, going back to the top here. What happens in the circuit physically, now that we've talked about it in terms of the equation and seen that it's possible to get an oscillatory behavior? We saw that before time 0, everything was at rest here. There was no current, no voltage. And then at time 0 plus, we couldn't have a sudden change in the current because of the inductor. And the capacitor also did not like a sudden change in voltage, which then led to the conclusion that all the input voltage had dropped momentarily and instantaneously across the inductor. So now you have an inductor with that voltage. Okay. Now, if an inductor has a voltage, what does that say about its current? It has to change, right? Because V equals L di by dt. An inductor can't have a voltage and keep it there without any change in current. Now, the current in the circuit at that moment was 0. But the inductor says, well, you forced me to have this voltage. It means I'm going to have to change the current. So the inductor will start forcing a current through the circuit. Once you have a current in the circuit, and by the way, V was positive in this case, right? Same as V naught at that moment. So it means di by dt would have to be positive, which means the current I has to grow, starting from 0. So now you have to have a slightly positive current at the moment just after t equals 0 plus, which means you start to charge up the capacitor. And at the same time, you start developing a voltage across the resistor too, because there is a current in the circuit now. Which means the voltage across the inductor will have to be smaller now, because the resistor will start taking up some voltage. The capacitor will start charging up. And so you will have this behavior continuing, where the inductor voltage starts decreasing and the capacitor voltage and the resistor voltage start increasing. And in fact, you can think of this as, well, as the capacitor is being charged up, it's starting to collect energy. And this continues. Now, if the circuit had very small resistance, if R was very small, what would happen is that you would go to a case where the capacitor gets fully charged, and then it will start discharging back, and you would go back and forth between the inductor and the capacitor. And because they're both elements that just store whatever energy, you know, whatever energy they take from the circuit they store, they can give it back to the other element and go back and forth. But once you put the resistor in, it will start consuming some of that energy and turning it into heat, which will actually eventually leave the circuit, radiate out of the circuit, conduct out of the circuit. And so as these oscillations are happening back and forth between the capacitor and the inductor, every time a little bit of the energy is wasted in the resistor. And that's why the oscillation will gradually die out. Now, if the resistor is really, really large in its resistance, then it will waste so much of that energy that you will not even be able to complete one full oscillation cycle. And that's why you have that critically damped situation and eventually overdamped. So you will not see oscillations anymore. So this sort of, in a qualitative manner, what happens in the circuit. Okay? But of course, to start to feel that and appreciate it, you will have to do some examples with numbers. So that's what I want to do now. But how are we doing time-wise? Yeah, I think it's a perfect point for a 5-minute break. And actually, there's a question, and then we'll take a break. Here's a very good question. Are there specific things that we can look for to identify that a circuit is second order? Now let's look at how this circuit became second order. It was really the consequence of the fact that the voltage of the inductor was proportional to the derivative of the current, and the voltage of the capacitor was proportional to the integral of the same current. So there were 2 orders difference there. This happens very often when you have more than one element that has time dependence, capacitance or inductance. But you have to be careful not to generalize that too much. For instance, if you have 2 capacitors that can be combined to be replaced by 1 capacitor, then you would not see this. Or you could have a circuit that is complicated enough that looks like it has an inductor and capacitor, and you would expect this, but maybe something is shorted out somewhere that you won't see this, right? So yes, for a simple standard circuit, you would expect that if you have an L and a C, you would see this. But I don't want to generalize it too much. Okay. All right, so let's take a break. Thank you. So let's do another example. Example with some numbers. So this is a circuit that I'll draw here. At t equals 0, the switch opens. So that's 6 ohms. This is 0.5 Henry. This is a capacitor with a capacitance of 0.02 of a farad. And this is 3 ohms. Let's call this V. And this is I. So we had this circuit sitting for a very long time with the switch closed. This is t equals 0 up here. At t equals 0, the switch opens. So that branch gets disconnected. So we want to find I of t for all time. And if I say I of t question mark, I mean to imply for all time. So again, we had the circuit sitting for a long time with the switch closed. Now remember how in the previous case I said when I wanted to analyze t less than 0, I said assuming that we had reached a DC steady state. And I hope, having seen the solution now, that even if you have, when you do have resistance in the circuit, even if you have that oscillatory behavior, eventually it dies out, then that DC steady state condition makes sense after a very, very long time. Okay? So for t less than 0, again, I'm going in the same order of steps. So for t less than 0, my circuit looks like this. Things are connected, and I have a DC steady state. And the switch is connected. This is a fixed battery, 10 volts. So that is not changing. It was just a switch. Now, in DC steady state, what does the capacitor do? The capacitor becomes like an open circuit. We've seen this several times. So the capacitor has effectively become an open circuit, which means there is no current going through it. It doesn't mean that there is no voltage drop across it. There could very well be a voltage drop between these two nodes. The inductor, on the other hand, has become like a short circuit, which means there is no voltage drop across it. But of course, there could well be a current going through it. So capacitor like open circuit, inductor like short circuit. Okay. And we have the values of these resistances, 3 ohms here and 6 ohms here. So now this is a pretty simple circuit to solve, I hope, because this middle branch is actually disconnected. So there's no current going through it. And if you wanted the current that we had called I up here, now you have a simple KVL. So let's call this plus minus V4 and plus minus V6. And we know this is what we called V up there. And this is, so the inductor has a 0 volt drop. So I'll write that here, 0 volt. And the capacitor has a 0 amp going through it. And let's call this this one plus minus V3. And so we know that V3 is going to be simply 0 because there is 0 amp going through it. But we have one big KVL on the big loop that will give us minus 10 plus V4 plus V6 equals 0. And I'll just replace then minus 10 plus. Now, what is the current going here through the V4, through the 4 ohm resistor? It's the same as I because there is no current branching off because of KCL at that node. So this is also I. So this is plus 4 times I plus the other one is 6 times I equals 0, from which then I conclude that I is 1 amp. And from there then I conclude that I conclude that, sorry, got distracted. V4 is 4 volts and V6 is 6 volts. And we also know that V3 equals 3 times 0, and that's 0. Okay? I think that's it. What is V in this case? What is the voltage V? So let's do a quick clicker thing. What is the voltage V? Let's see what we got. Okay, very good. It's very reassuring. So indeed, the answer is 6 volts, and that comes from, for those of you who had difficulty with it, just write a KVL here, and you'll see 0 volts here, V6, which was 6 volts, and 0 volts here. So V will have to be 6 volts also. So another KVL. V also, 6 volts. So that's it for t less than 0, and that continues all the way until t equals 0 minus. So you have these values for t equals 0 minus. So those are the values up to and at t equals 0 minus. Okay? Now at t equals 0 plus, so going to t equals 0 plus, again, you know, we haven't really done anything specifically second order yet. All these things that we are talking about are a way to practice for similar situations in first order circuits too. So at t equals 0 plus, we have to identify what the things are that we can carry from 0 minus. So now at 0 minus, I had this situation. For the capacitor, what is it that carries over from 0 minus to 0 plus? Is it its voltage or its current? It's voltage, because it doesn't like a sudden change in the voltage, right? So V of 0 plus will have to be the same as V of 0 minus. Because it's a capacitor. which does not like a sudden change in voltage. On the other hand, for the inductor, what is it that carries over? It's the current. It doesn't like a sudden change in the current. Now, the current, I, was 1 amp. So because of the inductor, I of 0 plus is I of 0 minus, and is 1 amp because of the inductor. Notice the voltage and current here, V and I, are for 2 different elements. I'm not concluding because I have V equal this that I have that. That one comes from the capacitor up there. This one comes from the inductor. They have nothing to do with each other. Now I can solve the circuit with this knowledge. But recall that at 0 plus, now the circuit has changed because the switch has been opened, and that left side branch has become disconnected. So all I have left is the capacitor and inductor and those 2 resistors. So the circuit is like this. I have my 6 ohm resistor here. I have the capacitor here. I have a 3 ohm resistor here. So this is 3 ohms. This is 6 ohms. And I have the inductor here. And I said that the current here is 1 amp. Notice only for the time t equals 0 plus. I'm not propagating yet. And the voltage across the capacitor only at that point in time is 6 volts. Okay. What did we call these? So to be consistent, V3 and V6 and V. So that's V equals 6 volts. This is V3. And this is V6. And let's call this VL. And this is half a Henry. So how do I deal with this now? This is a snapshot in time. At t equals 0 plus, we concluded that at that moment only I have 6 volts between these 2 nodes across the capacitor. And I have 1 amp going through the circuit. Now, if I have 1 amp here, it's straightforward to calculate the voltages of the 2 resistors. But knowing the current only at that moment in time will not tell me the voltage of the inductor. How should I calculate the voltage of the inductor? Any suggestions? So that's correct. VL is always LdI by dt, but I don't know the I by dt at that moment. I know only I. So it won't help me. It's a correct statement, but it won't help me. KVL. Look to the circuit for help. Because I know I can get the voltage across the 2 resistors. And I also know the voltage of the capacitor at that moment. So I'll use KVL. So at t equals 0 plus again. OK? At t equals 0 plus, so I want to really emphasize, this is only for that point in time. So V6 of 0 plus is simply 6 times 1, and that's 6 volts. OK? What is V3 at 0 plus? Who says 3? Who says something else? What should it? Minus 3, thank you. Look at the current. This current that we are talking about is 1 amp going this way. The way I have defined V3 in the circuit, it so happens that its polarity is the opposite of our current convention for the way we normally do the V equals Ri. Okay, so this is a very, very good example of the subtleties here that you have to be careful with. You see, if I had defined V3 the other way around, if I had defined it with the plus side at the bottom, then that V3 would have been 3 volts. This V3 is the negative of that. Okay, V3 at 0 plus is minus 3 times 1 equals minus 3 volts. You can also think about it in another way. You know that there is this 1 amp current going like that, right? Equivalently, it means that there is a minus 1 amp current going downward, which means V3 is minus 1 times 3, which is the same answer. Okay? So now let's write a KVL. Knowing those voltages, we'll find the inductor voltage also, if we are interested in it, which we will eventually be interested in. But for now, just for the sake of completeness. So at 0 plus, I have minus V3 plus, minus V plus V6 plus VL equals 0. So let's just plug those things in. Minus, now V3 itself happens to be minus 3. Minus V, which is 6, plus V6, which is 6, plus VL of 0 plus equals 0, which then means VL of 0 plus is simply minus 3 volts. Okay, which is in fact, you can see from the circuit, because if you have 6 volt drop across the capacitor and there is a 6 volt drop across the first resistor, then the drop across this resistor has to be equal to the drop across the inductor, right? Well, that's the KVL in spoken words. So now I know how things are at t equals 0 plus. And from here on out, I want to write the differential equation for how things evolve in time. For the rest of t greater than 0, now I don't, these values are not going to stay there. These were for only 0 plus. For the rest, I'm going to have to write the full thing. And so again, let's draw the circuit. You notice I'm not saving on drawing the circuit. I'm not saving paper here. Because redrawing it is actually greatly helpful. You might think it takes time, and it does take a little bit of time, but that 30 seconds that it takes to redraw it will save you a lot of time in confusion later. So it's a very good practice to draw it. So this is 6 ohms. And so we call this V, and we call this I. Now these are time-dependent functions. We call this V6. We call this VL. We call this V3. So everything is well defined. And I'll write all my equations. Well, KCL, again, is trivial because it's implied, and that's why we have chosen the same current for all of these elements. They share the same current. So KCL has been implied. It's implicit. KVL is like what we wrote up there. Minus V3 minus V plus V6 plus VL equals 0. And then the elements give me for the capacitor. Now, what should I write for the capacitor? The current I and voltage V, how are they related? So the capacitance is 0.02. And everything is in standard units, so I won't write the units inside the equations. So C dV by dt, correct? Who agrees with that? Who disagrees with that? There is a negative sign there. Very good. Because, again, look at the way the current I is defined. For this particular problem, the way things are defined, the current I is the current that goes from the negative to the positive side of the capacitor. So in the equation, it has a negative. For V6, I have simply 6 times I. For the inductor, I have 0.5 di by dt. And for V3, what can I say? Again, remember the way the current I is defined, it's going from the negative to the positive side. So in this case, minus 3I. So these are the element relationships. And if you plug them in the KVL equation, you will see that things are in terms of I. Now, again, the first equation, you would have to take that integral to write it in the form of V in terms of I. Okay. Now, remember in the previous example, the parametric example, I did that, and then I had to take a derivative of both sides to get rid of the integral. So another way, maybe more convenient, would be to take the derivative of the two sides of the KVL first, and then plug things in. Maybe that's easier. So, but same thing, no difference. So if I take the time derivative of my KVL equation, I'll get minus dv3 by dt minus minus dv by dt plus dv6 by dt plus dvl by dt. And now I'll replace, and I won't have to deal with an integral. So minus dv3 by dt, the time derivative of this is simply minus 3 times di by dt. And I have this additional minus here, not to be forgotten. So minus 3 di by dt. Then minus dv by dt. Now look at the first equation, the capacitor current, I equals minus 0.02 dv by dt. So from there, I have minus dv by dt directly. And so that would be I divided by 0.02. So that's simply plus I divided by 0.02 plus dv6 by dt, which is plus 6 times di by dt. And finally, plus dvl by dt. And again, here going back to the question we had earlier, you see where that second order derivative comes from. The fact that you had both the capacitor and the inductor. So plus 0.5 d by dt of di by dt, which will give you the second derivative. So this is your equation. Now let's rearrange a little bit and add things up. So I will write it in this familiar form, which means I'm dividing both sides by 0.5 or multiplying by 2. So this will give me plus, I had 6 plus 3, which is 9, so plus 9 times 2, which is 18 di by dt. Plus so I have 1 over 0.02, but I have to multiply by 2. So that's 1 over 0.01, which is 100 I. Okay. Could you guys please verify that I've done this correctly? So this is my equation. And now I have real tangible numbers to work with. So going back to the formula for the solution to the equation there, you see that whatever multiplies the first derivative, we called it 2 alpha. And whatever multiplies the function itself, we called it omega squared. So my 2 alpha in this case is 18. So alpha is 9. And omega square is 100. So omega is 10. What is the unit for alpha and omega? So this is second derivative of current with respect to time, right? So the first derivative would be amps per second. The second derivative would be amps per square second, right? So to get that here, these should have a 1 over second unit, right? Does anyone know how we call 1 over second? Hertz, right? So this is of inverse time, a nature of inverse time. Now, omega is an angular frequency, so you might say radians per second. But anyway, the dimension is 1 over second. Okay, so which case does this correspond to? Alpha is 9 and omega is 10. So alpha is smaller than omega, assuming I did the math correctly, which you will verify at home. Alpha is smaller than omega, so this would be an underdamped case, and we can define this frequency, right? By the way, this omega is called natural frequency. I think I didn't write it there. So omega is natural frequency. It's the frequency that you would have if there was no damping. And alpha is damping factor. So we have an underdamped case, so we'll calculate omega d. Okay, alpha is smaller than omega, so this is underdamped. So my omega d is the square root of omega squared minus alpha squared, which is the square root of 100 minus 81. Now, what is the square root of 19? That's maybe about 4.5, shall we say, approximately. 4.5 inverse seconds. So you have omega d, and you have alpha, and the gamma was 0 in this case, so there's no constant. So your solution then will be of this form. I of t will be m1 cosine of, let's say 4.5, again approximately 4.5 t, plus m2 sine of approximately 4.5 t, and this whole thing damped by e to the minus 9 t. And there's no constant because there was no gamma. Okay? So this is the form of the solution. The time constant for the decay of the envelope is 1/9. And the frequency, the angular frequency is 4.5 radians per second approximately. How do I get M1 and M2? Initial conditions. Now I need two initial conditions for this because I have two unknowns. Need two initial conditions. One would be I of 0 plus, right? The value of the function itself at the beginning. The other one would be the value of the function's derivative, di by dt, at point 0 plus. If I have these two, I can put them there and solve for M1 and M2. So I'll go back to where we came up with I of 0 plus. There you go. I of 0 plus is 1 amp. We had it before. So it's good that we had the foresight to solve the problem at 0 plus. How about di by dt of 0 plus? Where do I get that?
Use VL at 0 plus?
Absolutely. We know that for an inductor, you always have VL equals L di by dt. And you remember how we calculated VL? Well, if we have VL at that point, it means we have di by dt at that point. So that is something that maybe better written here. So I can say di by dt at 0 plus is simply VL by divided by L, right? Minus 3 divided by 0.5, which is how much? Minus 6 amps per second. Okay? So that's why I calculated that VL at that point t equals 0 plus, so that I could directly relate it to di by dt at 0 plus. Okay. Now having that, I will go to here. So that was how much? Minus 6 amps per second. And I itself was 1 amp, right? Now we've got a couple more minutes. I'll start plugging in. If we run out of time, you can continue on your own at home. But so from that equation, 1 I of 0 plus is simply, if I put 0, well, the exponential term disappears. And I have m1 cosine of 0, which is m1, plus m2 sine of 0, which is 0. So then I can say directly that m1 is 1. Okay? But then I need di by dt. And so for the first one, I have minus 4.5 m1 sine of 4.5, times t, plus 4.5 m2 cosine of 4.5 t. So the derivative of this times e to the minus 9t plus the derivative of e to the minus 9t times that first term. So which is then minus 9 e to the minus 9t times what we had there, which was m1 cosine of 4.5t plus m2 sine of 4.5t. And please verify that I'm doing this correctly. And so at 0 plus, again, things will be a lot simpler. di by dt, if I put 0 in there, the exponentials will be just 1, and the sine terms will disappear. I will simply have 4.5 m2 cosine of 0, which is 1, minus 9 times m1, again, cosine of 0 is 1. I think this is correct, but please verify. And so m1 I already have. So I'll put di by dt at 0 plus minus 6 equals 4.5 m2 minus 9 m1, and m1 I already have up here as 1, minus 9. So finally, m2 becomes 9 minus 6, which is 3 divided by 4.5, which is, can you verify that's correct? And the unit of these, of course, should be amps, right? So, because it's a current we are dealing with, amps. Please verify. So then my complete solution will be just putting these in. M1 is 1, and I'll put approximate because that 4.5 was approximate. So I of t is approximately cosine of 4.5 t plus 2/3 sine of 4.5 t e to the minus 9t. And this is in amps. Don't forget the units. And if you plot this, you will see that it has a behavior that's oscillating with this angular frequency of approximately 4.5, but with a time constant of 1 over 9, right? So it's approximately 1/10 of a second. Okay? So now here's something fun that you can do at home. Go plot this with a computer and see the graph, okay? But please verify, okay? I did this quickly. I hope I did this correctly, but verify at home. Thank you.